Okay, we are going to talk about vectors. And when I see you in class on Thursday, then we'll kind of jump right into using these. So bear with me. This lecture or this lesson is just purely a math lesson. I'm not really going to get into the physics at all yet, and I'm not a math teacher by profession. So go easy on me. But we're going to start just with reviewing a little bit of right triangle trig, just to make sure some of those things are coming back to you, and check the settings on your calculator. And then the goal for this lecture is to get into a little bit more concretely what a vector is. So I've been talking about it, we've used the term, but it's been a little bit abstract so far. And then we're going to focus in on finding the components of a vector and adding multiple vectors, because those are two skills we will use in physics going forward. So let's start just with a brief right triangle trig review. So I know you guys are all in different math classes kind of coming into this course, and I believe that you have all seen some right triangle trig before. So because I'm just going to go real fast, like just quick review how to find a missing side and quick review how to find a missing angle. If this is something that does not feel comfortable for you, please do email me or talk to me after class, and we can meet one-on-one and go over it a little bit better. Okay, so a lot of times when we use these vectors that are coming along, if you can picture a right triangle, a lot of times we know what we'll call the hypotenuse and then an angle. So I might know, like, this is 11 meters and this is 35 degrees. And for various reasons, I want to find these two sides. So because I would call this side X and this side Y. Doesn't really matter. You can call it whatever you want. And so we can use some just basic trigonometry, right? I'm talking SOHCAHTOA, that level of basic, to be able to figure out these missing sides. Now, one thing that you'll notice is I am using degrees here. So there's two ways to measure angle, so to speak. One is degrees and the other is radian. So in physics, we are primarily going to be using degrees, which means when you have your calculator, you need it to be in degree mode. So let's start there. So remember, my calculator is older than you, no joke, but I think it's about the same. If you go to the right of the second button, hopefully it looks similar, there's a button that says mode. And if you go down to mode, it's going to be automatically set in radian mode, actually. So if you go down to mode, so press mode, the third line down for me, and I think it's the same for you guys, says radian or degree. So you want to scroll down and click to highlight the degree instead of radian, and then just hit second mode to quit, and then we'll carry on from there, okay? So make sure that you are in degree mode before you do any of this work. Now, unfortunately, for the girls in this course who are in pre-calculus or calculus, those courses are going to use radians a lot more, and I'll use degrees. So I'll just keep reminding you, like, check your mode, check your mode. But that's going to be an important thing. You'll notice, you'll start to get some really crazy answers. So you should notice if you're in the wrong mode. But make sure that you're just, like, keeping track of that as you do assignments in those different courses. Okay, so back to my right triangle. Here I have a right triangle. I know an angle. I know one of the sides, the hypotenuse, as I said, and I want to find these missing sides. Okay, so let's start with X. I want to find X. If I look at this right now, I know this angle and I know the hypotenuse. X is adjacent to the angle, right? So if I think about my trigonometric function, sine, cosine, or tangent, I would choose the cosine because of the adjacent. So I can say the cosine of 35 degrees is equal to the side adjacent to it, which is X, divided by the hypotenuse, which is this thing I know, 11. I leave the units off when I'm actually working with the trig. Just, I don't like to confuse it with another variable. So we could say X, our unknown side, is 11 times the cosine of 35 degrees. Now in physics, because we want to know the real quantity, a lot of times I'm trying to find like an actual velocity or an actual displacement. You're going to put that in your calculator, so don't leave it like this. You're going to put it in a calculator and get an approximate value. I get about 9.01. So if this were meters, as I said, this would be 9.01 meters, okay? And then to find y, now that I know two sides, I've got a couple of options. So one option, I could use the Pythagorean theorem. So I can say x squared, which I now know, plus y squared is equal to 11 squared, right? That a squared plus b squared is c squared. You saw that probably geometry, maybe even like junior high. So I could use that to solve, or I can use a different trigonometric function. So that's what I'm going to do just because we're reviewing that. So I could use tangent because I know the adjacent and I want to find the opposite, or I could use sine. I'm going to use sine. So I'm going to say the sine of 35 degrees is equal to opposite, which is y, divided by hypotenuse, which is 11. So y is equal to 11 times the sine of 35 degrees. And that gives me about 6.31 for that other side. Now you're going to see as we go, in physics, often we see this correlation between cosine and x and then sine and y. Depending on what math class you're in, you may have seen that before. If you haven't, it's okay. But you'll notice that pattern. A lot of times when I'm finding a horizontal component, I'll use that word in a minute, component, I'm going to be using the cosine, and when I'm using a vertical, you'll see me using the sine. But there are times that can switch. So don't take it for granted. Be careful. Look at your triangle. Use that SOHCAHTOA and just see, like, okay, what's adjacent? So in this case, x was adjacent. What's opposite? Okay, let's look at the other thing that we sometimes need to do, and that's find an angle. Okay, so let's say that instead of knowing the angle and the hypotenuse, let's say I know x and y, I need to find the angle. So that also happens often with this vector physics. So let's say, I don't know, I'm making this stuff up. Let's call it 6. Let's call this 4. And let's say I want to find this angle. Again, it's often the angle between, this doesn't really matter, but you'll see that as I go with physics. It's often the angle between the horizontal and the hypotenuse that I like to work with. Okay, so I want to find this angle theta. That's an unknown angle. Okay, and so if I look at this right now, I know two sides for theta. I could go find the third side. I can use Pythagorean theorem and go find that hypotenuse if I want, but I'm not asking you to do that. I'm asking you to find this angle. And so right now, the two sides that I know are opposite and the adjacent side. And so if I think about my three trig functions and I know the opposite and the adjacent side, that is going to steer me towards the tangent, right? So I'm going to say the tangent of theta is equal to opposite, which in this case is 4, divided by adjacent, which is 6. 4, 6, which we could simplify if we wanted to. So the problem here is I'm not asking you to find the tangent of theta, so I can do that. But what I'm asking you to find is theta. I want you to isolate theta. So to get that theta by itself, you need to take the inverse tan of both sides, right? So like the inverse tan of the tan is 1. So this is what I'm doing in my calculator, basically. Like so, okay? So over here, this becomes 1. That just isolates me to theta then. And over here, to get that inverse tan on your calculator, you're going to hit second tangent. And that will give you about 33.7 degrees. So you hit the inverse tangent button, which is second tan on your calculator, and then put in whatever you have here. So I just put 4/6. And that's how we could find a missing angle. Now, once I know one angle, so what was this again? I forget, 33.7-ish. And I know that this is a right, so 90-degree angle because I have a right triangle. I can go find the other angle if I were asked about it, because we should know that there are 180 degrees in every triangle, right? And so we can just use that to find the third angle if we needed it. Okay, so that's it for my review of right triangle trig. Again, if you need more help, please let me know. More that was just to sort of practice what you do in your calculator to get those values. Let's jump into vectors. Okay, so I defined vectors actually in the first chapter we did, Unit 1, so the one-dimensional kinematics, and we talked about the difference between vectors and scalars. So vectors are numbers with magnitude and direction, versus a scalar is just a number with a magnitude. So in the world of physics, we said like distance is an example of a scalar. Like I can just say, oh, I drove 100 miles. I don't tell you, this doesn't tell you where I went. Did I end up back at home? Did I go north, south, east, west? Did I leave the state? Who knows? I drove 100 miles. So the odometer, which shows the mileage on your car, is an example of a scalar quantity. It's just giving you the straight up number of miles you drove, and that's the only information you have. A vector quantity has that magnitude, so it still tells you that, but it also gives a direction as part of the number. And so that direction is really important to get right. Now you were working with vectors in the last chapter. So velocity is a vector, displacement is a vector, acceleration is a vector. So when we were doing the kinematic equations, besides time, all the quantities in the kinematic equations were vector quantities. So you were working with them. However, it was pretty easy to do, and I didn't really have to talk as directly about some of this vector math because we were working with motion only in one dimension. So the way we were indicating direction was with that plus and minus sign, right? Remember I said if it's going to the right in x, we're going to call it positive. If it's going to the left, negative, and same deal for the y. And so we were using those signs, and they were very, very important in our numbers. And if you didn't put the sign in correctly, you would oftentimes not get the correct answer because the sign, again, is part of the number. So the signs were making those quantities vectors, and I was able to look at a sign, for instance, a negative velocity, and say, okay, I know this thing is falling down, or I know this thing is moving to the left. Now, we are moving from one-dimensional motion into two-dimensional motion, and then from there we're going to get into forces, and even some rotation and some electricity and magnetism, and all of those things involve working with vectors in a little bit of a more complex way. So, you know, as I mentioned in the last chapter, it's not very realistic that motion is all just this way or just this way. It's often a mix of the two. So when we get into vectors, we have to be able to handle looking at a vector that has two dimensions to it. And there's actually three-dimensional vectors, there's four-dimensional vectors, and modern physics gets into crazy stuff like there could be 11 to 14 dimensions. That's a topic for another day. But we're today going to look at two-dimensional vectors. So actually what I just drawn, those right triangles, are what a two-dimensional vector would look like. So if I, let's go to my weekend. I drove to Columbus. We met my mother-in-law at a state park in Columbus. And so from my house, we took 71. And actually to go from like the Cincinnati area to Columbus looks kind of like this, right? And the park, I'm simplifying, but the park was about 100 miles away. So that's what my drive looks like. My displacement was 100 miles, and it was a little bit to the northeast. Now, to describe it more succinctly, not just saying it was a little bit to the northeast, I would have to give this thing an angle, right? So I need to say exactly what direction I was headed. I don't actually really know for Columbus, sorry, but I'm going to make it up. I'm going to say that this was about 70 degrees, okay? So from my house, this is my house, to this park, I can't draw parks, so there's the park we went hiking in. I drove 100 miles, approximately 70 degrees north of east, okay? Now, I could take this and I could figure out exactly how many miles I drove that were north and how many miles east. And that's what we call the components of this vector. So when we have a vector, we can take that vector and we can split it down into its components, into its pieces. So the one piece here, let me get a different color. I draw these pieces head to tail. You see that term in the notes, and I'll describe it better in a minute. But here's, oh, this is a terrible marker, isn't it? I can tell my kids got into it. Let's see about this one. That's much better. Okay, so that's how far east I drove, and that's how far north I drove, right? And these two vectors, when placed head to tail, make up the resultant, is what we say. Now, I just threw out a whole bunch of terms that I have not yet described. Okay, so let's go through some of these terminologies. Okay, so components. I have been sort of saying that. So components. Components are, you can think of as the pieces of the vector in each direction. So this is again, a two-dimensional vector. It's going north and east, two directions. And so the components are how far east it's going and how far north it's going. So as we get into two-dimensional motion, some of the motion will be in x and some of the motion will be in y. And so the components are like the x and y. I'm going to call them x and y components. So these are the components of the vector. This 100 miles, that's what you'll hear me calling the resultant. That's the resultant. So the resultant is like that total vector. So when we describe something in resultant form, it would be 100 miles at 70 degrees north of east. That's the resultant. If we described it in component form, I need to go find these components, but I would say how far east and north it goes. Okay, so let's go find those components. And it's actually just what we just did. We're just going to use right triangle trig to do it. So if I wanted to find, I'm going to call this my x component and this my y component. So if I want to find my x component, I have this 70 degrees, right? X is adjacent to that. So I'm going to say the cosine of 70 degrees is equal to x over 100 miles. So x is equal to 100 miles times the cosine of 70 degrees. And that is equal to 34.2 miles. And then if I want to find the y component, y is opposite this 70 degrees, right? So if I think about my trig functions, opposite over hypotenuse would be the sine function. So I'm going to say the sine of 70 degrees is equal to y over 100 miles. So y ends up being 100 times the sine of 70 degrees. And so when I put that in my calculator, I get 93.97 miles. Okay? So, going back to our terminology, the components, the pieces of this displacement are that I drove when I was headed up to that state park in Columbus, 34.2 miles east and about 94 miles north, right? So I can take this total displacement and split it into its pieces, its components. The resultant form of that is just describing the total displacement. In some, I don't know where you would learn about this in math. In math, you learn about two different types of coordinates. Cartesian coordinates and and by the way, as this is going, if you've not heard of polar, it's coming in your future and this will prepare you. So don't stress if you've never heard of that. Okay, so I'm thinking you've heard of Cartesian and polar coordinates. Cartesian coordinates are describing a point in space, a point on a graph in math, with x and y, and that you could get three-dimensional and say z. So if I give you an x and a y point, like I say 2 and 1, you could graph that, right, on a graph and figure out where it's at. The polar coordinates could tell you the exact same location with different kind of coordinates, and that's called r and theta. So this r being the radius and theta being the angle from the origin. This is like when I'm doing things in component form, which is what most of what we'll do. And this is when I'm doing things in resultant form. So if you think about this, if I put this on an XY graph, my trip to Columbus, here's my little coordinate system. So that's a y axis. Forgive me for it not being straight. This is my x-axis, right? And I'm describing my, steps on my calculator. And I'm describing my trip to Columbus. If I described this point right here where I ended up at the park in Cartesian coordinates, it would be point 34.2, let's just round it to 94, right? So if I gave you a graph and said, plot this point 34.2 and 94, you would end up right here, and that was my park in Columbus. So you use the components, the x and y components, to get there. If I instead asked you to, and it's appropriate sometimes to do this, to do it in polar form, I'm going to use the word resultant form. You'll hear me say resultant. Then you would say, I would say, oh, I drove 100 miles at 70 degrees north of east. You would plot that, get a protractor out or whatever, and end up at the exact same point, right? So it's just two different ways of describing the same place. And in physics, again, I'm not really talking about the physics yet, this is a little bit more mathy, but in physics, there are times when either or and sometimes both are appropriate. Okay, so that is, in a nutshell, kind of how we can work with a two-dimensional vector. Now, the other thing you're going to notice that the term that's in your notes is head to tail. You see me say head to tail. When you are adding vectors, so in this place, I'm not really teaching you adding yet, but I'm putting an x and a y together to get a resultant. So when you're adding vectors, you're placing the vectors head to tail. So what does that mean? When we draw vectors, we use an arrow to indicate a vector. You see me drawing arrows all over the place. And so when I'm going head to tail, if you just, I start here at the origin. So here's the tail. The head is where the arrowhead is, right? So this is the tail, and I hit the head. And then the tail starts here for the next vector, and I go to the head. All right, so just think of like following a map. That's how I think of it. So it would not be correct if I'm drawing my x and y vectors to be like this. That's like tail to tail, so that's a no. But instead, you see the head go right into the tail of the next vector. So head to tail, that's what that means. Now, if I'm going to get the resultant, just write this down, and it will make more sense when we actually do some together today as you're taking notes, and then Thursday in class. So for now, just write it down. When you're getting the resultant of vectors, of x and y components, the resultant goes from the tail of the first to the head of the last. That's how you figure out where the resultant is pointing. So again, just write down for now. The resultant of the vectors goes from the tail of the first to the head of the last. So in this case, there's a resultant. It starts here. This is the tail of my first one, which was x, and it goes up to the head of the last right here. So that's what I mean by head to tail. Okay, so let's get into addition of vectors. Now, as I add the vectors, it's going to feel a little bit long. I'm going to say by 2 weeks from now, 2 weeks from whenever you're watching this video, you will be able to add vectors in 3 to 5 minutes with no problem. So it feels long at first, but it's really quite easy. Okay, so in physics, often we have multiple vector quantities, whether it's displacements or velocities or whatever. And we need to be able to, forces, actually that's a huge one, forces. We need to be able to add those vectors. There are multiple ways to add vectors. One's like super geometric. It's called the parallelogram method. We are going to use what I think is the easiest method, and so that is addition of vectors by components. So that's what I'm going to teach you right now, addition of vectors by components. Okay, so let's add two vectors. So let's say I went walking, and I walked two distinct directions. So first I walked 4 miles, 30 degrees north of east, and then I walked 7 miles. This is a heck of a walk, my word. 7 miles at 40 degrees south of east. And so the question is, where did I end up? So I'm going to add these two vectors to see where did I end up. So the first step, this is more for me and my learning style. You may not need this. The first step I always say when we're adding vectors is to draw the vectors on an XY coordinate system just so you can visualize them, like what direction they're pointing in. So I'm not drawing them head to tail or anything like that. I'm just putting them on an XY axis so I can visualize. Now, I'm using north, south, east, and west here. Hopefully you know which direction those things are pointed in. And so the first one, I'm not going to get out a protractor and measure or anything like that. I'm just kind of eyeballing it. 4 miles north of east. 30 degrees north of east, that's something like this. So this is the first vector, 30 degrees. So I'm going to write a little, just so I know that's vector 1. And then the second vector, again, I'm not doing the head to tail or anything, just putting it on this thing. So I'm going to draw it coming from the origin, so I can picture it. 7 excuse me, 7 miles of 40 degrees south of east. So that's down here like this, 40 degrees, 7 miles, and so that's south of east. So, sorry, I'm gonna write a 2 so I can remember that that's vector 2. So some of you may not need to take that step, but if you're a more visual person, some may find it helpful just to see which it's pointed. Another thing people might do, so I'm going to do both here, and you do not need to do both. Some people just draw each vector separate, make a little triangle out of it. So I'll do that as I go into the next step. The next step is to find the x and y components of each vector. So we're going to take each vector, and the terminology we would use is we're going to resolve it into its components, into its x and y components. Okay, so that 4 miles, this is the way you could just draw it as a triangle. You say I have 4 miles pointing northeast, 30 degrees. This is its x component, this is its y component. Okay, so I'm saying x1 and y1 because this is vector 1. So I'm going to use sine and cosine to find those, those missing sides. So x is adjacent to the triangle, so I can say the cosine of 30 degrees is equal to x over 4. So x is equal to 4 times the cosine of 30 degrees. I'll get the answer in a minute. And the y is opposite the 4. So I can say sine of 30 degrees is equal to y over 4. So y is equal to 4 times the sine of 30 degrees. Now, I'm going to go be careful here, and change it to x1 and y1 since this is for the first vector. And actually, cosine of 30, some of you should have that memorized, depending on your math class. We multiply that by 4, it's about 3.46 miles. And the y, we know that one in our heads, 2. Okay, and then I'm going to go do the same thing for the second vector. So the second vector was pointing down like this.
We don't have any clothes.
Okay, you just have to wait to change. Let me finish the lecture. Or sneak in your room and get one. Alright, it's at 40 degrees. And so this is x2. Sorry, kids just got home from school and want to change. Go. And y2. And so we can say the cosine of 40 degrees is equal to the adjacent x2 over the hypotenuse. And use that to find x2. And y2, as you can see, you're going to end up using a sine. So I'm running out of room, so I'm just going to write it. y2 is equal to 7 miles times the sine of 40 degrees. Oh no, my calculator just died suddenly. How could it die live on film after 20 years? That's a doozy. Oh, it's been saved. That was a scary night. Alright, cosine of 40 times 7. Wait a minute, went into radian mode when it died there. Okay, 5.36, sorry for the delay, for x, and y, 4.5, almost exactly. Okay, so it seems a little bit long, but it's a pretty simple step. You're just taking each vector that you have and breaking it up into its components. You're finding the horizontal piece and the vertical piece. You're just using right triangle trig to do that. Again, you see sort of this pattern developing where I'm using cosine most of the time to find x, sine to find y. Now, what you do need to do is your next step, once you've got all these components, is check your sines. This 40 degrees, really on a unit circle, this 40 degrees is 320 degrees. And I'm not dealing with that, and I didn't type it in that way. And so what you need to do is look at your vectors and decide, is the x component positive or negative, and is the y component positive or negative. And you decide that based on the rules we were using in the last chapter. So if it's to the right in x positive, if it's up in y positive, opposite makes it negative. So let's look at this first vector. This first vector in x, we would say, is it pointing left or right? And it is clearly pointing to the right. So this would be positive. You don't need to write the positive. I just kind of do that to remind myself I thought about it. And in y, we say, is it pointing up or down? And it is pointing up, so that is positive. So both components for the first vector are positive. The second vector in x, it is pointing to the right. It's still pointing east, so the x component is positive. And in y, we would say it's pointing down, so negative. Okay, so just recapping what we've done, we've drawn our vectors, we have found the components of each vector, and we check the signs to see if those components should be positive or negative. Finally, we add all of our x's and all of our y's to get our totals for each component. So we say x total is equal to x1, which was 3.46, plus x2, which was 5.36. And y total would be y1, which was 2, plus y2, which was negative 4.5. Okay, so we get an x total of 8.82 miles, and we get a y total of negative 2.5 miles. Finally, our last step is to put these two totals together, head to tail, and find our resultant. Now, this tells me right here in Cartesian form, this tells me what my total is if I've added these vectors. So my total, you remember this, so I was walking 4 miles in one direction and 7 miles. I have ended up 8.82 miles east and negative, so we'd say 2.5 miles south. That's where I've ended up. However, if I wanted to say, like, how many miles total did I end up from my starting point, then I need to put these two things head to tail and find the resultant. So I'm going to do that right now. So I always start with x. It's addition, it doesn't really matter. So x is positive, so I'm going to draw it going to the right. So 8.82. Y is negative, so I'm going to draw it going down. Now you don't have to write the negative, you just have to draw it going down. And that takes care of that. So here I draw my two vectors, my two total components, head to tail. The resultant goes from the tail of the first to the head of the last. So this is my resultant. Now, remember that r and theta, you need both of those quantities to talk about this. So r would be, you're going to use Pythagorean theorem to find it. R is just the third side. Theta is going to be the angle between r and the horizontal, so between r and x, okay? Now I'm running out of room, but to find that r, I'm just using the Pythagorean theorem. So we can say x squared plus y squared is equal to r squared. So I'm going to take this down here. So r is equal to the square root of 8.82 miles squared plus 2.5 miles squared. And when I plug this in, I get you're being very patient. Hopefully you're still watching. This is a long lecture, sorry. I'm almost there. About 9.17 miles. So I've ended up on my walk 9.17 miles from my starting point. And then I need to find this missing angle. You can use any, you know, all three sides. So you can use any trigonometric function to find the missing angle. For whatever reason, I have a preference personally. I just like sine. I don't know. I just love sine. So I think because I eventually like using the law of sines. So I'm going to say the sine of theta is equal to opposite, which is 2.5, divided by the hypotenuse, which is 9.17. Now remember, to get that theta by itself, you need to take the inverse sine of both sides. So I'm taking the inverse sine of 2.5 divided by 9.17, and I get 15.8 degrees. So in my long walk, I've ended up 9.17 miles at 15.8 degrees, and look at my triangle. This tells me what direction. Southeast. Southeast. So my resultant is somewhere like here. And that makes sense. It's kind of right between the two, a little bit more skewed to this one, and that was the bigger mileage, so that makes sense. Okay? So, recapping again, and then I'm going to do one more really fast. And the final word problem we're going to do together in class on Thursday. So, recapping again, when you are adding vectors, you want to in some way visualize your vector, whether it's this or the drawing the triangles or both. So, you're going to visualize your vector. You're going to find the x and y components of each individual vector. You're going to check your signs for the x and y components. You're going to add those components to get an x total and a y total. And then you're going to put the x and y totals together, head to tail, to find the resultant in polar form is what we're doing there, okay? So we're going to do one more. This is the world's longest lecture, I know, but this one I'll go quick. I'm going to pick up the speed on this process. We're going to do one more. We're going to add 3 vectors. I'm going to put one right on an axis to make it easier. And I'm not even going to put units on this or anything. It's just going to be 3 straight vectors that I put on the xy coordinate system. Okay. So here's my coordinate system. Okay, so vector 1 will be 5 at 45 degrees. Vector 2, right on the x-axis, and that is 6. And vector 3, let's put it straight down, and let's make it 7. I didn't really draw this to scale very well at all. Okay, so this is a little bit different because 2 of the vectors are right on an axis. Okay, so that's vector 1, vector 2, vector 3. Now, when you're adding 3 or more vectors, there's really nothing different about the process. I'm just going to have one more set of x and y coordinates, or components. So, I'm going to follow my same process. So, I've drawn all 3 vectors. I'm going to find the x and y components of each vector. So, let's start with vector 1. So, x is adjacent to the angle. So, we can say that the cosine, sorry, I almost wrote sine. Cosine of 45 degrees is equal to the adjacent, which is x1, divided by the hypotenuse, which is 5. So x1 is equal to 5 times the cosine of 45 degrees. And we can say that the y, this vertical piece, if I were to draw that, is opposite. So we could say the sine of 45 degrees is equal to y1 over 5. So y1 is equal to 5 times the sine of 45 degrees. Now, I hope you know, maybe not, cosine and sine of 45 degrees are actually the same. So you might have looked at this and said, oh, they're actually going to be exactly the same x and y, and that's fine if you want to skip that step. All right, so there we go. And when we plug the numbers in, I guess let me get the actual value. Oh my gosh, my calculator's doing some funny things. Today might be the last day of its life. 3.54. Okay, vector 2. Let's go look at vector 2. Vector 2 is sitting right on the x-axis. So when it's sitting right on the x-axis, it is all in x. You can think of this as 180 degrees. The cosine of that is -1. The sine is 0, if you want to think about it trigonometrically. Or just visualize it. So it's all on x. So we would say the x component is 6, and the y component, I didn't mess with signs yet, I just wrote the value. The y component is 0. There is no vertical piece to that. So that's easy. We don't have to do any trig. And the same thing goes for that third vector. So if we look at the third vector, this one is all in y. It's pointing straight down in y. So we would say there's no x component to that. The x piece is 0. The y piece would be that 7. Now, let's go check the signs, because I wrote everything in as positive, and that's not necessarily true. So, first vector is pointing to the right. It's pointing up and to the right. So, x will be positive because it's pointing to the right, and y is also going to be positive because it's actually pointing up. Second vector is pointing straight to the left. That is negative an x because it's to the left, and 0, 0, so we don't have to deal with that. The third vector is pointing straight down in y, and so that means that 7 should be negative. So I have all my components. I found this, check the signs on them all. I'm ready to find my totals now. So my x total, this is where it's just slightly different. I'm just adding 3 things to get my x total. So 3.54 plus negative 6 plus 0, actually there's no piece to that third one. And my y total is equal to 3.54 plus 0 for the second one, plus negative 7 for the third one. So this gives me an x total of negative 2.46 and a y total of negative, oh, that's embarrassing. It's just one more. Negative 3.46. Sorry, I went into autopilot and put that in my calculator. Okay, so I have my x total, my y total, and my final step is to take these two, draw them head to tail, and find my resultant. So my x is pointing left, which makes it negative. My y is pointing down, which also makes it negative. I'm sorry, it is negative, so it's pointing down. And so if I'm going to find the resultant of that, I start excuse me, at the tail of the first, point to the head of the last. The angle I want to find is the angle between the resultant and the x, so that's this angle. And again, I just use Pythagorean theorem to do it. So r is equal to the square root of x squared plus y squared, which gives me a resultant of about 4.25. And theta, again, choose your trigonometric function that you want. I would say the sine of theta is equal to opposite 3.46 divided by the hypotenuse, 4.25. I'm going to take the inverse sine of both sides. And so that gives me an angle approximately, oh my gosh, this calculator, 54.5 degrees. Now, it's drawn, like what direction? 54.5 degrees. It's below the negative x-axis. Just look at the way I drew the triangle, or south of east. So if I add these 3 vectors, I end up with an answer that's pointing kind of down like that. And that makes sense. That seems feasible, especially when you look at the magnitudes. It makes sense. Okay, so that's it. You survived. This was quite a long video. You are troopers. And I will see you in class Thursday, and we're just going to pick up and start doing this right away. So I'll see you soon.